Linear or tangent line approximation. Here is a graph of the function y equals fx. Here's the value where x equals a, and here is the tangent line to the graph of the function fx at x equals a. The point is afa, and the slope of the tangent line is the derivative of the function at x equals a, or in short, f prime a. Because we have the slope and the point, we can use the slope-point equation, simplify, and to get that the equation of this tangent line is y equals f of a plus f prime a times x minus a. Let x to be almost a. It is a plus dx when dx is very small. We would like to approximate f of x plus dx. We are going to do so by using the tangent line at x equals a instead of the graph itself. As you can see, this value is the approximated value for f of x plus dx, but this is exactly the value of the tangent line that we have here below at the value where x equals a plus dx, because we are considering the tangent line at x equals a instead of the graph of the function itself. We can conclude then that f of x can be approximated by f of a plus f prime a times x minus a, which is exactly the value of the x on the tangent line, which is f of a plus f prime a times x minus a. It is a good approximation only when dx is small. It means that a and a plus dx are really close to each other. Here's the dx, and here is dy. It's the approximated difference between f of x plus dx and f of a. The linearization of a differentiable function fx at a is Lx equals f of a plus f prime a times x minus a. If you can recognize this, Lx is exactly the equation of the tangent line to the function at x equals a. Again, the reason is because the slope is always the derivative of the function at x equals a, and the point is afa. Here is the point-slope equation of the line, and we just simplify a little bit. We just add f of a to both sides, and we get that. Example. Find the linearization of the function fx equals x to the power of 2 plus 1 at x equals 1. The function is x to the power of 2 plus 1. We need now to find the derivative of the function, which is 2x, and the value of a here is 1. Pay attention, a is always a value of x. F of 1 is 2, and f prime of 1 is 2. We are using this formula, which is again, this is just the equation of the tangent line to the curve y equals x to the power of 2 plus 1 at x equals 1. We will replace f1 and f prime 1 by 2, and we get, after simplifying, that L of x equals 2x. The linearization of f is used to approximate the value of f of x by evaluating Lx, meaning evaluating the value of the tangent line at x instead of evaluating the value of the function at x. Example: find the linearization of the function f(x) equals x cubed at x equals 2 and use it to approximate f of 2.01. We need to know the function. It's x cubed. The derivative is 3x to the power of 2. The value a is 2. Now we have to substitute 2 in the function. We get 8. In the derivative, we get 12. And now we combine everything to find L of x. We do the algebra. We simplify. And we get 8 plus 12x minus 24, which is 12x minus 16. Now let's do the other part. This linear approximation is supposed to work really nicely to values which are almost 2, because the linearization was about x equals 2. To approximate a value which is almost 2, like the value at 2.01, we can just substitute 2.01 instead of the x, so it's 12 times 2.01 minus 16. And after we do the math, we get 8.12. It means that the value of the function at 2.01 is almost 8.12. We can roughly check that. We know that f of 2 is 2 cubed, which is 8. So this is supposed to be about 8. This is true, obviously, only if the function is differentiable, because otherwise this is not true. But if the function is differentiable, then we know that it's also continuous. And what happens in this case is that the value of the function at 2.01 is supposed to be about the value of the function at 2. Now I want to show you this in the graph. Here is the graph y equals x cubed, and here is x equals 2. Let's see what is the tangent line there. Here is the tangent line at x equals 2, and the equation of the tangent line is 12x minus 16. And what is the meaning of what we just did? If we will now like to value at f of 2.01, it's really a complicated number. So instead of that, I'm going to take the value of 2.01 in Lx, not in fx, but in Lx. So I get this graphically. This is what we get. As you can see, it's a little less than the real truth. So in this case, the linear approximation is smaller than the real value because the tangent line is under the graph of the function, as you can see. I want to show you what happens if the tangent line is above the function, like in this function. If this is a, this is f of a, here's the tangent line at x equals a. So what happens now if we will use the linearization instead of the function? You can see that now we get more than the function. In this case, the linear approximation is larger than the real value because the tangent line is above the graph of the function. If we use the tangent line and it's above, we get more. Be careful. The choice for A depends on the function. It is a nice number for f, the function you have to approximate. fa should be easily evaluated. Example: approximate the square root of 8.5. The function here is square root of x, so the nice number is going to be 9. So a is going to be 9, because square root of 9 is 3. Example: approximate cubic root of 8.5. Now this is the function, and clearly a equals 9 not going to work, but we are going to choose a equals 8, because cubic root of 8 is 2, very easy to evaluate without calculators. Be careful. The idea of linear approximation is that the exact value of fx is unknown, so you cannot use f of x in your approximation. As you can see, we have here f of a and f prime of a. The only x that appears here is just this one. Linear approximation is a trade-off. It is easy to evaluate, definitely without calculator, but it's not exact. Example: approximate the square root of 3.99. Now we have to figure out everything. So the function is square root of x. The nice value of x, which is the a, is a equals 4, because square root of 4 is just 2. Now we're ready to do everything. This is obviously the x. It is the nasty number. It's number which is not nice, and that's why we have to approximate that. If it was nice, we wouldn't have to approximate. F of a is this, which is 2. F prime is 1 over 2 square root of x at x equals 4, which is 1 over 2 times square root of 4, which is 1 over 4. And here's the formula. Again, f of x can be approximated by whatever is written here. It's just a tangent line to the curve of y equals square root of x at a equals 4. We substitute everything. We're evaluating everything. And we get 2 minus 1 over 400. The meaning is that the square root of 3.99 is approximated by 2 minus 1 over 400. Makes sense? Square root of 4 is 2, and this is almost 2.